Hello, this is a project presentation. My name is Haodong, and the project title is a KUZUSHIJI-MNIST classification by using CNN. The contents will include the 5 parts, and let's start with the task. The goal of this project is to classify 10 kinds Japanese handwriting characters. The dataset we used is a KUZUSHIJI-MNIST. It has 17,000 pictures, and every picture is 28 minus 28 pixels. The 60,000 of the pictures are the training datasets, and the others are the test datasets. And why we choose CNN as a tools to do the classification? We use the MLP to do this task, but the hidden layer in MLP only have the perceptrons. Though it is more simple and the MLPs have less parameters, but the limitation of MLP is cannot provide the power to feed the data well. So even if CNN is more complicated and it has more parameters, we use it because it has the most powerful convolutional layer. As we can see, the convolution layer is when you put an image into this model, through the filters we can get a map from the original image, and we call this map as a future map because this map is fully used the locally connectivity, and this map can represent the original image well, and we always use this to do the classification or other tasks. So the CNN model in our project is like this. We use the convolutional layer, max pool layer, and the fully connected layer in the head layer. And the kernel size of convolutional layer is 3 minus 3, and the kernel size of max pool layer is 2 minus 2. That's because the image is not so large, so we can choose the small number of the kernel size. And the activate function in the head layer is a ReLU function. The output activation function is a softmax function. And we use the cross-entropy loss function as a loss. It is a loss function that calculates the different classes between output and desired level. So it's very common in classification task. And the optimizer we used at begin is a stochastic gradient descent, also called SGD. And after we fixed our architecture, we want to choose some hyperparameters. We can see this formula. This is a SGD, which is the which is a formula represent the wind update processing. So the next wind is decided by the previous wind, the learning rate sigma, and the batch size n, and the gradient of the wanted and the input. So we can learn that from this formula, the batch size and the learn rate will have a great effect on the wind updated processing. So let's accept this kernel as a learning curve kernel. This is loss function, and this is epochs. Through the epochs, the loss is decreased to a local minimum, and but if the hyperparameters not decide so well, the end of the training this model will be this point. But if we choose the hyperparameter well, we will keep decreasing to the global minimum. So how we choose the batch size? Well, before we choose this hyperparameter, we fix other hyperparameters such as the learning rate, the optimizer. We choose just one variations. So we can see that the line, the blue line is a first line who reached the highest, but the green one is a line that can reach the highest. It means that it can reach the best accuracy on the test set. So we choose the batch size as 16.4. And when we fixed the batch size is fixed 64, we change the learning rate at these values. As we can see that the blue one is the first line that reached the highest, and the highest, also called the best accuracy, is also close to the green one. So we choose this blue line as the learning rate. So the learning rate will be 0.0001. After we fixed the hyperparameters in the model, there are still some ways to improve our performance. One of them is we can add the dropout layer in the model. So when the model have too many parameters, or the training datasets is not larger enough, there always be the overfitting problem, which means that the model is overfit the training data. So when it is used to predict the test datasets, it have very bad accuracy. So to solve this problem, we add the dropout layer after the fully connected layer. So the dropout layer can let the perceptron in the fully connected layer lose some of wind. In the case, the training process we used in that case the test dataset can be predict well. So when in this picture we can see that when we add the dropout, the test accuracy can increase more smoothly, and it can be a better performance of the model. And another way to improve the performance is to check the optimizer. So when we change the optimizer from SGD to Haodong optimizer, we can see that the validation accuracy can get higher, and it is just within less epochs than the SGD optimizer. So besides the batch size and learn rate variations, these two ways are usually used to improve the performance of CNN. So finally, we can get the confusion matrix of the predict process. This confusion matrix consists of 10 rows and 10 columns. The 10 rows is predict labels from 0 to 9, 10 classes, and the same at the columns is 0 to 9, 10 classes true labels. And we can see that every true labels class, the predict label number in this matrix. So we can calculate the test predict accuracy is 0.9489. So we can conclude that the best parameters in this project, we can say that the batch size equal to 16.4 and the learn rate is 0.0001, and the dropout layer can improve the generalization performance. It means that it can get a higher performance when we do the when they do the test set prediction. And the Haodong methods can lead to a better optimization than the SGD. Within less epochs, the Haodong optimizer can get a higher accuracy in the classification task. So let's show the code. We can see that in this project, we first is a function that pollute the confusion matrix, and this part we get the input dataset from the training and the test images, and then we fix the epochs and batch size, and then we build the models. After that, we compile the models with the optimizer, loss function, and the matrix we want to save. So after we build our models, we can train the models with the batch size, epochs, and validation datasets. After we feed the model with the data, we can predict the test image, and then we could plot the confusion matrix and the accuracy, test accuracy, and train accuracy. So we can see the model information through the and then it starts to training. We could see the confusion matrix. The train set confusion matrix and the accuracy. We can see that this is just one simple condition that the model, when the optimizer chose the add-on and the loss function chose the category cross trophy, and the epochs equal to 20, the batch size is set as 16.4. Every time when we choose a hyperparameter or change the optimizer, we could product the confusion matrix and the accuracy learning curve. So every time we do this work, and finally we could paint the learning curve and confusion matrix in the like the slides. So that's all. Thank you. Yeah, when the training is over, we can see the test and training accuracy and the loss lines. So we could see the confusion matrix. The train set confusion matrix and the accuracy. We can see that this is just one simple condition that the model, when the optimizer chose the add-on and the loss function chose the category cross trophy, and the epochs equal to 20, the batch size is set as 16.4. Every time when we choose a hyperparameter or change the optimizer, we could product the confusion matrix and the accuracy learning curve. So every time we do this work, and finally we could paint the learning curve and the confusion matrix in the in the like the slides. So that's all. Thank you.